Okay, hello. So this module is intended to overview a few basic concepts that you've probably seen in physics in the context of ENEE 2700 Circuits 1. So firstly, a couple definitions. So the definition of a circuit in this situation is a system of electrical components. We're going to talk about what those electrical components are throughout the semester, that are connected to one another. Specifically, it's a system of components connected to one another that form a closed network. Okay, so let's dive down into this definition a little bit further. So let's let this generic box be an electrical component, meaning that it can manipulate the movement of charge. Okay, we're going to model this component as having two terminals where we can model the behavior between the terminals or across the component. Okay. We'll get into the details of that in a moment. So given that electrical component, we can start connecting them together in a variety of ways. For example, seen here. Okay. So this by definition is what we call a network. In other words, an interconnection of these components. A circuit specifically is when we create this interconnection of components, a network. A circuit is a subset of a network that consists of at least one closed path. So in any of these networks, we can define points that are making these junctions between electrical components. For example, and here in red, we can call that point A, here point B, point C, point D, just spots in the network that are the ends of components or the interconnection of components. So a circuit by definition means that we can start at any point in this network and walk around the network back to that point without going through the same element more than once. So likewise in the bottom example, if we label these points, which we're going to call nodes eventually, A, B, C, D, E, and F, we see that, for example, if we start at A, B, C, or D arbitrarily and go in an arbitrary direction, we can find a closed path that we can get back to A without going through any of the elements more than one time. Okay, so this is what we mean by a circuit. In the top example, you can't start at any of the nodes and get back to itself without going through an element more than one time. So that is not a circuit. It is still a network, an interconnection of elements, but it doesn't consist of a closed path. I should also note that in this bottom example, this network consists of a circuit, shown here, also with a network. That does not form a closed circuit. And then finally, the point of this course is really to study the behavior of these circuits. Okay, so now on to some basic concepts, specifically the idea of energy and power. We're going to first define them in what you've used to seeing them in with physics, and then we'll relate those to the quantities that are of interest to us for electric circuits. So first, work or energy, same thing. We're going to use the symbol W for that to denote the variable of energy. So we know that energy is mass times acceleration times distance. If we expand that out and using the SI units, SI unit for mass is kilograms, acceleration meters per second squared, and distance is in meters, we get that the units of work or energy must be kilograms meters squared per second squared, and this has a special name called a joule, of which we use capital J to denote. Okay, so next is power. Power is defined as the rate at which work is performed. So anytime we see the word rate, we imply that the function is a derivative with respect to time, so it's a time rate of change. So power is going to be denoted by the symbol P, and we know that it's going to be the first derivative of the work with respect to time, so dW over dt. And we know that the units of work is in joules, units of time is in seconds, so units of power is joules per second, and we call that a watt, W-A-T-T, which we use the symbol capital W for. And from this equation we see that 1 watt is going to equal 1 joule per second. Okay, a couple of things about notation here. So I used the symbol P for power, and I noted that that was the first derivative with respect to time. So in reality, power is a function of time, so I should be writing it as script P as a function of time, shown here. We'll often simplify this a little bit by merely removing the function of time. So anytime you see the script version of the variable, as in this case, we're implying that this is a function of time. Even though I'm not writing the parentheses with a t inside of it. This is going to be in contrast to when I use capital of the same variable, in this case. This is still denoting power, but I'm implying that the power is constant with respect to time. Both of them are denoting the quantity of power. Just one is implied that it's a function of time, shown in the top, and one is implied to be a constant. This is going to be true for any of the symbols and variables that we use throughout the course. Okay, so on the last slide I noted that the SI units when computing energy, so it's just worth making sure you are familiar with what those are. Here's a picture of them. These are in the first chapter on table 1.1 of the textbook as well. And likewise, familiarize yourself with the SI prefixes as well. The common ones that we'll see in circuits are probably going to be giga, mega, kilo, milli, micro, nano, pico, and femto. Okay, so let's test your ability to convert units as well as apply the concepts of power and energy. So here's an example where a lamp is running at 60 watts, so it's a 60 watt rated light bulb. If the lamp is always on, how much energy is consumed per day? So at this point you might want to pause the video and try to work it out yourself, and then you can follow along with my solution. Okay, so we know that power is the first derivative of work with respect to time. Therefore, energy or work can be found as the integral from 0 to some time point t of the power as a function of time. Since in this case power is constant, we can rewrite this as just being power after some time point t. Maybe we'll put time point t0. Okay, so we want energy per day. So that's going to be in units of joules per day. So we can do this a few ways. We can just apply unit conversion techniques to compute this. In other words, multiplying power times time in order to get the units of per day. See that work per day is equal to the power, which is in units of joules per second, times 60, which seconds for every minute, times 60 minutes in every hour, times 60, times 24 hours in the day. And of course power is 60. So we do that multiplication and we end up with 5.18 megajoules per day. Mega being 10 to the 6. Okay, so let's do another example. What is the weekly cost if energy costs 12.5 cents per kilowatt hour? So firstly, in this example, I've got a new unit here. I've got this unit called kilowatt hour. We know kilowatts is a unit of power. Kilowatt hour is actually a unit of energy, so it can be related to joules. So we're taking power multiplying by time, which is the hour here. And this is really used for big numbers of power. The power company is going to charge you in kilowatt hours, and it's so that we don't have really huge numbers of joules to deal with in our calculations. Simple as that. So to look at what a kilowatt hour is in terms of joules, we can simply look at the conversion of power of 1 watt is 1 joule per second. So we can look at, if we multiply to, we can convert to per hour by multiplying by 3,600 seconds per hour. So that gives us that 1 watt is 3,600 joules per hour. So then the unit 1 watt hour would just be 3,600 joules. So we multiply 3,600 joules per hour times 1 hour. And then moving on, 1 kilowatt hour is going to be 3,600 times 10 to the 3 for the kilo joules. In other words, 3.6 times 10 to the 6 joules, or 3.6 megajoules. So 1 kilowatt hour is equal to 3.6 megajoules. Okay, so in this example, we're looking for energy firstly used for a week. So that can be expanded as the energy used in a day multiplied by 7 days in the week. So that's going to be 5.18 megajoules in the day, which we computed before, multiplied by 7 days per week, which is going to give us 36.3 megajoules used every week. And then we need to convert that to units of cost. So we can take the energy used in the given week and then convert to kilowatt hours, because our energy per week is megajoules per week. So we'll take that, multiply by the cost of 12.5 cents per kilowatt hour, and then the unit conversion of a kilowatt hour into megajoules, which we did on the previous slide. Performing that multiplication out, we get 36.3 megajoules per week times 12.5 cents per kilowatt hour times 1 kilowatt hour divided by 3.6 megajoules, and we can see that megajoules and megajoules cancels, kilowatt hours cancels, leaving back cost per week, which is going to work out to be 125 cents every week, or $1.25 per week to run that lamp.